So good morning, everyone, and welcome to the Mathematics Consortium Distinguished Lecture Series. This lecture series is conducted by the Mathematics Consortium, IIT Bombay, TIFR, and ICTS. We are very happy to have today's speaker, Professor Rekha Thomas. She will talk on graphical designs. A few words of introduction. Professor Thomas did her PhD in '94 from Cornell University under the supervision of Professor Strumfels. As you remember, he was also one of the speakers in this series. She spent her postdoctoral fellowship years at Yale and Berlin, and then she joined Texas A&M University as assistant professor, and later she moved to University of Washington, where she is a distinguished professor currently. Professor Thomas is author of a very popular book in the AMS student library. It's called The Lectures on Geometric Combinatorics. She was inaugural fellow of the American Math Society in 2013, and she was also a plenary speaker in the International Symposium on Mathematical Programming in 2012. She works in multiple areas: optimization, applied algebraic geometry, computational algebra, operational research, computer vision, combinatorics. So it's very interesting to read her papers, which mix many of these things together. If you want to listen to a mathematician talk about a theorem for half an hour, there is a podcast called My Favorite Theorem. And she talks about the Eckhart-Young theorem in a very interesting way, which comes in the singular value decomposition. Professor Thomas is a well-known researcher and a great teacher, and we are really delighted to have her speak in this series. So, Professor Thomas, you may begin your talk.
Thank you, Jigal. Thank you, everyone, for coming. It's always hard in the mornings to organize these things, so I appreciate it. Okay, so I would like to tell you today about something called graphical designs. This is an area of research that I have been working on fairly recently, and the whole topic is actually also fairly recently defined by an analyst called Stefan Steineberger. And I will tell you what they are and some of the results that we can prove about them, as well as maybe towards the end we can talk about why they are, how they are used in different places. Okay, so this picture you see in the front slide is an example of a graphical design, but I will explain what the definition is and how you work with them. Okay, so this is joint work with. This joint work with my PhD student, Catherine Babecki, here at the University of Washington. Okay, so let me start by the motivation for this concept called graphical designs. So they were motivated by the notion of spherical designs, which is a classical object, and maybe you know about this, but let me roughly tell you what they are. So a spherical quadrature rule is a set of points on the sphere, so x1 through xn on s to the d, along with some weights. So you put weights on these points such that if you have a smooth function for some sufficiently smooth function f, the integral of the function on the sphere, so the global average of the function on the sphere, is roughly the same as the weighted average of the function values at these points x1 through xn. Okay, so this is what's called a quadrature rule. This is a standard object in numerical analysis, numerical integration, and so on, where you want to integrate some function over some continuous domain, but on the computer especially, you want to find some discrete set of points with weights so that the weighted average of the function values is the same as the global average or the overall integral. Okay, so this is a quadrature rule. And on the sphere, the most interesting function is to integrate our polynomials. So from the theory of spherical harmonics, it turns out that the thing you want to really integrate are what are called harmonic polynomials, and which are just restrictions of general harmonic polynomials onto the sphere. And here you're interested in points that can do this kind of averaging for all polynomials up to some degree. So for example, a spherical T design is a set of points that can integrate all polynomials of degree at most T, okay? So of course, as you increase T, the number of points you need increases. And on the left-hand side here, you see an example of a spherical 5 design. So these are the vertices of an inscribed icosahedron inside the sphere. And they're very symmetric and the weights are uniform. And in this case, these 12 points that you see on the sphere are enough to integrate all polynomials of degree up to 5. Okay, so this is the notion of spherical design. It's a very standard and important topic in numerical integration. Okay, so the question now is that was asked by this analyst, Stefan Steineberger, is whether we can extend this definition to the domain of graphs. Okay, so nowadays a lot of functions are discrete, and graph data especially is very important in the context of data science and so on. So how can we pass to graphs? Can we make an analog of spherical designs or quadrature rules, but now on graphs instead of some continuous domain? Okay, so let me start by how we should think about integration. Okay, so let's start with a graph G. It has some vertex set V and some edge set E. It's some finite graph. It's simple, meaning it has no loops and no multiple edges, and it's connected. Okay, so very nice, simple graph. So we're going to say that a subset W of the vertex set, along with some weights, which I will call A sub W, will say that it averages a function on the graph. So a function on the graph is just a real valued function on the vertices of the graph if you get this equality that you see here. So on the right-hand side, you see the global average of the function on the graph. So just sum up all the function values, divide by the number of vertices. And on the left-hand side, you see the weighted average of the function values on just the subset W. Okay, so instead of integrating, now we are averaging, which makes sense because we just have a finite set of things to work with. So let's just do a very simple example just to make sure that this concept is clear. Okay, so on the right here, you see the Peterson graph, and on the left is a function on this graph. So it takes these values, 1 on vertex 1, 0 on vertex 2, -1 on vertex 3, and so on. So I've ordered the vertices in some way. It's not written here, but let's assign these function values to the vertices. If you look quickly at this function, you will see that its average value on the graph is 0. Okay, so if you add things up, you see 1 minus 1 cancels out, 1 minus 1 cancels out, 2 minus 2, and then -1, 1. So the average value is 0. So what we're looking for is a collection of vertices, a small collection, such that the weighted average on that collection is the same as the global average, which happens to be 0. Okay. So here I show you two examples. So on the right, on the left, you see these red points, and they are weighted with just the weight 1/5. We could have just weighted them with weight 1 if you want. So it's uniform weights. And now if you take the average of the weighted average of the values on these red points, you see you have 2 times 2 plus -2 plus -1 plus 1. So that average is 0. Of course, I have to weight it with this 1/5, but since the average is 0, it doesn't really matter. So the global average of the function is the same as the weighted average on these red points. Okay, so this is an example of this subset W that we're looking for. And here's another one. So this one has one vertex with weight 1. Okay, the red vertex has weight 1. And all these pink vertices that you see here have weight 1/3. Okay, so they're different weights. And again, if you take the weighted average of the function on these colored vertices, you will see that the value is 0. Okay, so 1/3 times 1 plus 1/3 times 1, so that's 2/3 plus another 1/3, so that's 1. And then -1 is getting weighted with weight 1. So altogether it cancels out and you get 0. Okay, so these are the types of subsets W that we're looking for. Right. So the next question to ask is, which function should you average? So on the sphere, the thing that we were trying to average were polynomials, starting with low degree polynomials and increasing the degree. But on a graph, what are the right functions? What are the right functions to average? Or in other words, is there sort of a notion of smoothness, because we want to try to get the smoothest functions first and then move upwards from there. Okay, so for the rest of this talk, let's assume that the graph is regular. So this means that every vertex has the same number of edges touching it. And in this case, it turns out, it turns out that the functions we're going to try to average are exactly the eigenvectors of a matrix associated to the graph, which I will call AD inverse. Okay, so let me explain what this is, and then I'll tell you why these are the right functions. So A is the adjacency matrix of the graph. So it is a 0, 1 matrix whose size is the cardinality of the vertex set times the cardinality of the vertex set. So it's a square matrix. And the way you assign its entries is you put Aij equal to 1 if and only if the ij is an edge in the graph. So everywhere there's an edge, you put a 1 in the slot ij. And if there is no edge between I and j, you put 0. Okay, so it's a 0, 1 matrix. And the D is just a diagonal matrix where on the diagonal you put the degree of the vertices in the graph. But our graph is regular, so that means that all these degrees are the same. So it's just a scaled identity matrix, this D, okay? So AD inverse is really the A matrix that has been scaled by the degree. So it's just a scaled version of the adjacency matrix. And we're going to average the eigenvectors of AD inverse, okay? So the reason why this is the right thing to do is, again, by analogy with the sphere. So in the sphere case, we were averaging these from spherical harmonics. The spherical harmonics are the eigenvectors of the Laplace operator on the sphere. And similarly, in the case of graphs, there is a Laplace operator. So there's the discrete Laplacian. And this discrete Laplacian has the same eigenvectors as the simpler matrix in the case of a regular graph. So I'm just going to use the simpler matrix. And so this is the reason why we are going to try to average the eigenvectors. And hopefully you'll see as we go along that this is very natural. Okay. So let me give you an example. So here on the left, you see the icosahedral graph. So it's the graph of the icosahedron, 12 vertices, several edges, I didn't count them. And then here you see AD inverse. So AD inverse is a 12 by 12 matrix. It has zeros down the diagonal because there is no loop. So II is not an edge. But then everywhere you see a number, there is an edge. So for example, in slot 1, 3, you see an edge. That means there's you see a number. So sorry, you see a positive number. So there's an edge between 1, 3. Okay, 1 and 3. So this is some symmetric matrix, and it has been scaled so that you see the degree of the graph in the denominator everywhere. Okay, so this is AD inverse. This matrix, if you look at it a little bit more, you'll see, well, first it's symmetric, so all its eigenvalues are real, but it's also doubly stochastic. So if you add up the rows and you add up the columns, you get 1. So that means the spectrum of the graph or the eigenvalues, they live between -1 and 1. Okay, so this is a Markov matrix or a doubly stochastic matrix. So the eigenvalues are nicely contained inside this interval. Okay, so let's look at the eigenvectors. So the eigenvectors are what we're interested in. So here I have listed for you all 12 eigenvectors of this AD inverse that you saw in the previous slide. So it's a symmetric matrix. So it has a full orthogonal set of eigenvectors. So there are 12 of them, and you see them in the rows of this matrix. So the first eigenvector comes with eigenvalue 1, and it's just a constant vector 1, 1, 1, 1, 1, 1. Okay. Then there are 3 more other eigenvalues for this matrix. They have multiplicity. So lambda 2, lambda 3 are these numbers, and then lambda 4. And lambda 2, for instance, has multiplicity 3. So there are 3 eigenvalues that you see in the 3 rows of this matrix, and so on. Okay, so there are 12 eigenvectors. They're mutually orthogonal. I have not orthonormalized them. Okay, so they're not unit vectors in the representation that I show, but they are orthogonal to each other. And the eigenvalues are here. Okay, so these are the functions that we're going to try to integrate. And let me note one more thing. If you look carefully at the way the eigenvectors are ordered, you'll see that they're not ordered in increasing order or decreasing order, right? They're actually ordered by absolute value. So 1 is the eigenvalue of highest absolute value. You see it here. And then these two eigenvalues have the same absolute value. One of them is here, lambda 2, and the other one is here, lambda 3. And then the next one has smaller absolute values, so it's in the middle here, okay? So the ordering that we're going to use is going to like jump back and forth like this, because we're going to go by absolute value. So that's the ordering, and I'll talk about this ordering a little bit more later. Okay, it turns out that this is also the right order. This ordering makes sense for this sort of notion. Okay, one more thing to note, as I said, the first eigenvector is trivial. It's the all ones vector. The other eigenvectors, so these eigenvectors, I'm going to call them F1, F2 up to Fn. N is the total number of vertices in the graph. The first one is just this all ones vector. You see it here, the all ones vector. And all the other ones are orthogonal to the all ones vector. They're actually mutually orthogonal, but in particular, they are orthogonal to the all ones vector, which tells you that the average value of all of those other eigenfunctions or eigenvectors is actually 0, okay? So this is very convenient, which is why we use regular graphs. It just makes all the average values of all eigenvectors except the first one equal to 0. So it becomes a number that we don't really need to keep track of, okay? So these are the functions that we're going to try to average. Okay, so why do we do this ordering? So this ordering is called frequency ordering on eigenvectors, and it is a proxy for smoothness. So let me try to motivate or at least show you by example that this makes some sense, okay? So here is the graph of, this is the contiguous United States graph. So there's a node for every state in the United States. There is an edge when two states share a border, okay? So it's not a regular graph, okay? So the first eigenvector is not the all ones vector. And the picture here is a picture of the first eigenvector in this frequency order, okay? So the colors here represent the magnitude of the various entries that you see in the eigenvector. So it goes all the way from red to blue, let's say. And you see that this first eigenvector is fairly smooth across the graph. So as you go across from one vertex to the next, there is not a lot of change, okay? So this type of a function I would call somewhat smooth. This is a smooth function on this graph. This is the first eigenvector. Here's a second one. Here's the second eigenvector. This is also not so bad. It's fairly smooth. You see the colors don't jump too much. It's fairly smooth. And let's move on. Let's go back to the 11th eigenvector. Here's the 11th eigenvector. And now you see that the colors jump all over the place, okay? So in this frequency ordering, you're actually getting eigenvectors sort of ordered by smoothness in this sense. And smoothness in this sort of very discrete sense, all we want is that the function value should not change too much as you move from one vertex to another vertex, okay? So this is what this ordering captures. And it makes some sense. It's a bit like doing Fourier analysis. So what we're trying to do is if we have some function on the graph, so for example, we have the rainfall function on the United States, then we expect that most of this function is composed of very low frequency eigenvectors. Okay, just like in Fourier analysis or as the singular value decomposition or whatever, you expect that the first modes occur mostly if your function is smooth. And then if as your function gets more and more oscillatory or non-smooth, then you see the higher frequency functions. So that's why we order these functions in this way. And what we're trying to do is to average the first few or as many as we can functions in this frequency order. Okay, so that's the reason for this ordering. And the eigenvectors are what we're going to average. Okay, so now I'm ready to tell you what a graphical design is. So we have our graph. The first thing we're going to do is we're going to order the eigenspaces according to how their eigenvalues are ordered in frequency order. Okay, so lambda 1 is the span of the all ones vector. It's always the lowest frequency. Then comes lambda 2, which is the eigenvector that has the next smallest, next biggest absolute value. So the eigenvalues are ordered from biggest absolute value to the smallest, but the eigenspaces are ordered in the opposite way. Okay, so this is so as you march up these eigenspaces, the functions are getting more and more oscillatory. Okay, so in the beginning, the functions are fairly smooth, and then they're going to get more and more non-smooth. That's the idea. Okay, so we order the eigenspaces. And then a K graphical design is a subset W inside V, the vertex set, along with some weights. The weights are real numbers. And their job is to average the first K eigenspaces with these weights. Okay, so W is set to be a K graphical design if it'll average all the vectors that live in the first K eigenspaces with these prescribed weights. So the weights is part of the data. So W and AW are what we're looking for. So this definition, as I said, is due to an analyst by name Stefan Steinberger. He defined this in 2018. The paper appeared in 2020. Okay, so that's what graphical designs are. And depending on the type of weights that you allow, you get 3 different types of designs. So either we have no restriction on the weights, the AWs are just real numbers, these are called weighted designs, or we insist that the weights are non-negative, these are called positively weighted designs. This is very attractive for people who do numerical integration. They really like positive weights. So this will be a big focus in this talk. And then thirdly, we can also insist that the weights are just 0 or 1. These are uniform weights, and we call these combinatorial designs. So there are 3 types of designs that are possible, and we'll see all 3 types. Okay, so let's do an example just to make sure the definition makes sense. So I'm back to the icosahedral graph. Remember, there were 4 eigenspaces, and suppose we want to average lambda 1, lambda 4, and lambda 3. Okay, so I put it in whatever order I want. This is not in frequency order. And I'd say, okay, I want to average these 3 eigenspaces. So on the left here, you see an example of a weighted design. This is an arbitrarily weighted design. It uses this vector. The pink-red vectors are all positive, and the blue vectors, the pink-red vertices have positive weights on them, and the blue vertex has a negative weight on it, okay? And these 5 plus 1, 6 plus 1, 7, these 7 vertices form a design. They form a 3 design, meaning that it can average all vectors in the first 3 eigenspaces here, lambda 1, lambda 4, and lambda 3, okay? Here's one where the weights are non-negative. So now, of course, all the weights are red and pink, which means that they're all non-negative. You need more vertices because we're imposing more conditions on the weights. And then on the extreme right, you see a combinatorial design, but this is only a 2 design. It cannot actually integrate lambda 3, okay? It cannot average lambda 3, it's only a 2 design. And that's because I'm insisting that the weights be 0, 1. In fact, there is no 3 design where you can only use these uniform weights. Okay, so these are examples of the 3 types of designs that I defined. There's one more type of design that we'd be interested in. So these are called extremal designs. And this means that if you take your eigenspaces ordered lambda 1 through lambda m, let's look for a design that can integrate everything except the last one. Okay, so it turns out that you cannot actually integrate everything unless you use the whole vertex set. So this is the best we can do. The best you can do is integrate everything except the last eigenspace. Such a design we'll call an extremal design, and this was studied by Konstantin Golubov, also the papers from 2020. And these kinds of designs also you will see in this talk. Okay, so these are sort of the best designs in some way, like because they can average everything except the last eigenspace. Okay, so let me just show you a few examples. So in the examples we saw, this design is extremal. It's an extremal design because it's averaging lambda 1, lambda 4, and lambda 3. This is also an extremal design because it's a 3 design. It's averaging the first 3 eigenspaces, but this one is not. This is only a 2 design, so it's not extremal. Okay. Right. Okay, so the questions we wanted to ask were, or once these initial papers came out, the questions that at least seemed interesting to us was, how does one compute these designs, right? If we were interested in finding these K designs, how do you actually find them? Can you find minimal K designs or even minimum K designs, the smallest K designs, if I fix K? K means that you want to average the first K eigenspaces, sorry. And then a third question we can ask is even more ambitious. Is there a way to actually organize all of these K designs together in some way? So these are sort of natural questions. And remember, these questions really mean the following. We're looking for some subset W with some weights, such that when you take the weighted average of the function, you get 0 for all functions that live in lambda 2 up to lambda k. Okay, so this 0 is just happening because we chose the graph to be regular. So the global average is 0. So that is very convenient. So we're just looking for W and AW such that for all eigenvectors in the first k eigenspaces, their weighted average becomes 0. The first eigenspace is special because it's an eigenspace spanned by 1, 1, 1, 1, 1. So the average of the function on that eigenspace is not 0. And in fact, any subset will work. So that's why we don't worry about the first eigenspace. We just care about lambda 2 up to lambda k. Okay, so these are the questions that we asked. All right, so maybe I can stop for a moment to ask if there's any questions, because now I'd like to tell you what the results are. Is the definition okay? Are there any questions on any of it?
So what do you mean by organize all K designs?
Yeah, I'll tell you in a second what that means. Okay, so I'm just asking, rather than looking at them as just individual objects, is there like some kind of structure we can put them on? And I'll show you in the next slide, you'll see what I mean.
Okay, yeah.
Okay, I'll continue then. Okay, good question. So let me answer that question right away. Okay, so in a way that seems to be the most difficult question. Like, is there a global structure to these designs? And turns out there is. Okay, so here's the main theorem. So the theorem is that the minimal positively weighted K designs. So I'm going to focus on these positively weighted K designs because they are, I think, the most interesting. So the set of all minimal positively weighted K designs are in bijection with the facets of a polytope. Okay, and I will explain what this polytope is and why this works, but let me just start with just a statement. So I'm saying that you can put the minimal positively weighted designs on the facets of a polytope, which I will call PK bar. So K is we're looking for K designs. The polytope is going to be indexed by K bar. It is the convex hull of some explicit set of vectors, which I'll show you what they are. And the bijection just says that if W is a K design, then the complement, the V minus W, those indices actually form the facet, a facet of this polytope. Okay, so this is roughly speaking what the theorem is. It shows you how to organize all these designs, and maybe the picture is more interesting. So in blue here is a cartoon of this polytope. And what I'm saying is that on the facets of the polytope, which are the biggest faces of the polytope, you can put every single minimal design, K design, okay? So on the facets, you see the minimal K designs, and on the lower dimensional faces, like these vertices, you see K designs that are not minimal. They get more and more, less and less minimal in the sense that they get bigger and bigger in size, but they still average K eigenspaces. So this is the theorem. This is what I mean by organizing these designs. So they live on the faces of a polytope. Okay, we're going to organize them on the faces of a polytope. All right. So let me show you. Okay, I'm going to show this to you in a few pieces because it's a little bit involved. So first, let me start by just telling you what the polytope is, and then later we'll talk about why it works. Okay, so let me first give you a recipe for constructing the polytope. So what you do is you go back to this eigenvector matrix, which we were calling U. Okay, so these are the eigenspaces of the different eigenspaces blocked out by these little rectangular blocks. And suppose I'm trying to look for K designs. The recipe is like this. So first you set, say, bold K to be all the eigenvalues from lambda 2 up to lambda k. Okay, so we're trying to get all the first eigenspaces. So put all these eigenvalues into one set and put everything else into the complement set. So k is lambda 2 to lambda k, and k bar is lambda 1, which is special. So we keep it with the outside part, and then all the other eigenvalues that we are not catering to. Okay, so there are two types of sets. K will be blue in my slides. So these are the eigenvalues I'm trying to integrate. I'm trying to integrate lambda 1, lambda 2, lambda 3, but lambda 2 and lambda 3, I color blue, lambda 1 and everything else I color pink. Okay, so I break my matrix into two parts, this blue part and pink part, and then we pull them apart. So the blue part is down here and the pink part is up there. Okay, so I pull the matrices apart. And then I focus on the columns of this matrix. This is extremely non-intuitive because the eigenvectors are the rows of this matrix, but we're going to be interested in the columns of this matrix. And the polytope that we care about is the convex hull of the pink columns. Okay, so that's the recipe. Okay, I'll show you later why this works. So again, the recipe is like this. You color the eigenspaces that you want to average blue, okay, except for lambda 1. And you color all the other eigenspaces pink. So this is, the first one is pink, and then everything that you don't want to average is also pink. Pull the matrices apart, and now switch to the columns. Okay, we were interested in the rows in the beginning, but now switch to the columns. And take the convex hull of the pink columns, that is this polytope, okay, pk bar. This is a generalization of something called an eigenpolytope that was defined by Chris Godsell. He's a combinatorialist from Waterloo, retired now, but he defined something called eigenpolytopes back in the 70s. And this what we are constructing here is a generalization of that notion. Okay, so let me show you examples first before we talk about why this works. Okay, back to the icosahedron. So suppose I want to average lambda 1, lambda 4, lambda 3. What we're going to do is lambda 1 and lambda 2 are the pink parts. Okay, so here I've colored the pink parts. And now we ignore the blue. And now you have to take the convex hull of all of these pink columns. Okay, now the first row doesn't matter because it's just saying that all the vectors have height 1, or they're sitting on some plane. So just ignore the first row. But we have to take the convex hull of these other 12 columns. And if you do that, you get the icosahedron back. Okay, so this is a big coincidence. It's not normally the case that you will get this. But here you see there are 12 columns. They're in 3 dimensions. When you take the convex hull, you get the icosahedron back. Okay, so that's the polytope P3 bar. And so our theorem says that take a facet. For example, this is a black facet here you see with 3 vertices. The complement of that facet gives you a 3 design. Okay, so the complement is everything marked in pink and red in the back here. And that is an example of a 3 design. So that's actually a minimal 3 design. So of course, in the icosahedron, there are many, many facets. I forget how many there are, but for every one of those facets, you will get a minimal 3 design. Okay, so that's basically what the theorem is saying. Here's another example. So here I've put the eigenspaces in frequency order. So this is the order that I had in the beginning. And suppose again, we want to average lambda 1, lambda 2, lambda 3. Okay, so the recipe says take lambda 1 and lambda 4, the stuff we don't want to average, but you keep lambda 1 in that, color them pink. So now the pink blocks are this and this. And now take the convex hull of all the pink columns. Okay, again, the first row is not important, but you have to take the convex hull of these columns over here. And now if you stare at these columns, you'll see they're all repeated. So here's a column repeated, here's one repeated, here's one, it's repeated here, and so on. So every one is repeated twice. So even though there are 12 columns, at the end of the day, there are only 6 things to take convex hull of. So take the convex hull, and you'll see it's just a 5-dimensional simplex. Okay. But so if it's a 5-dimensional simplex, then every facet is 4-dimensional. It has 5 vertices on it, but in fact, it has 10 vertices on it because every vertex appears twice, right? So there are 10 vertices on every facet. So the complement is just 2. So that tells you that the minimal 3 designs are going to have just 2 vertices. And you see the picture here, okay? So this is another example. Where you see this doubling, which is very useful because it actually reduces the size of the object that we have to look at. Here's another one where you see the doubling a lot. So this is a bigger graph. the truncated tetrahedral graph. Here, if we're trying to average the blue eigenspaces, you got to take the convex hull of the pink columns. But now you see the pink columns are just two-dimensional, right? Because we're ignoring the first one. It doesn't have really any information in it. So if you take the convex hull of all these columns, you're going to get some n-gon, right? Some polygon. And again, you see there is a lot of doubling happening. So 1, 0 is here. And in fact, 1, 0 appears 4 times. Every column appears 4 times. So at the end of the day, the eigenpolytope that we're constructing is just a triangle. Okay, so even though there are, in this case too, there are 12 columns, but each column appears 4 times. So the convex hull is just a triangle. And the theorem says, take a facet. So for example, here's a facet. Here are all the vertices that live on that facet. So the complement is 2, 5, 8, 10. And the 2, 5, 8, 10 gives you a design. Okay, so this is the theorem. The theorem says you can put all these minimal designs on the vertices, on the facets of a polytope. And I've shown you how you construct this polytope. Okay, so that's the theorem. And here's one more example, maybe not, we don't need to worry about this too much. It's the Peterson graph. And in this case, we're trying to average the first 2 eigenvectors, eigenspaces. So I have to take the eigenspace corresponding to the last one, which turns out to be this 5-dimensional object. It's more complicated. Here now the facets are not so simple. There are 22 of them. They come in 2 symmetry classes, and you see designs corresponding to them. Okay, so maybe the details of this one is not so interesting or important. Okay, so that is the recipe. Okay, so I've shown you the theorem and the recipe for how you construct the polytope. So now let me maybe explain why this works. Okay, so the reason this works is because of something called oriented matroid duality. And in oriented matroid duality, people care about configurations and their dual configurations. Okay, so in our case, let me explain it with the setup that I had. So in my setup, there was a blue matrix and a pink matrix. And normally they were turned so that the pink matrix was turned 90 degrees and sitting under the blue matrix, for example. But let's say we turn it like this. So the blue and the pink matrix has been transposed and put on the right side of the blue matrix. Now, if you think about what will happen now, you see immediately that these 2 matrices will multiply to give you 0, because remember, the eigenvectors are all mutually orthogonal. So every row of the blue matrix is orthogonal to every column of the pink matrix. Okay, so this is an example of 2 matrices that multiply to give you 0, and they have complementary dimension, meaning that if this is like d by n, then this is n by n minus d. So when you see a configuration like this, these blue columns and pink columns that have this property, they're called dual configurations. Okay, so we're interested in the columns of the blue and the rows of the pink. These are dual configurations, and dual configurations carry a lot of information. So here's, for example, one type of information it will carry. So here's an example of, say, pink matrix and blue matrix. If I transpose the pink, then it'll multiply against the blue to give me 0. Okay, so these are dual configurations. And let's interpret the blue columns as vectors. So for example, 1, 0 is a vector. So I've marked it with 1. The next vector is also 1, 0. So it's the same vector. So we double it and mark it with 2. The next one is -1, -1. It's marked here, 3. 4 is also -1, -1. And then 5 and 6 are 0, 1, 0, 1. Okay, so we interpret the columns of the blue configuration as vectors, and we interpret the columns of the pink configuration as a polytope. So the first column is all 1s. So just take the convex hull of the pink columns and you get the octahedron in this case, right? Because if you look at what's underneath this horizontal line, they're just all the different unit vectors with a plus sign and a minus sign. And if you take the convex hull, you get the octahedron. So the 2 configurations that we had gave you on the one side a vector configuration and on the other side a polytope. And it turns out that you can read off the facial structure of the polytope from the configuration on the other side. So this is a theorem. This is the main theorem that underlies the recipe that I gave you. This is called Gale duality in the situation of polytopes. And it says something, it says the following. So if you take an index set I in the set 1 through n, so this notation just means 1 through n, and you take the convex hull of all the pink vectors that are indexed by the complement of I, okay? So for example, so take the convex hull of the pink vectors indexed by the complement of I, then this is a face of the pink polytope if and only if 0 is in the relative interior of the convex hull of the blue vectors that are indexed by I, okay? So it's a little complicated, but what it's saying is that, let me show it to you an example. So let's say, for example, we take I to be 2, 4, 6, okay? So take I to be 2, 4, 6, 2, 4, 6 over there. So then this theorem says that if you take the convex hull of the pink stuff, that's indexed by the complement. So that's 1, 3, 5. Okay, so 1, 3, 5 is a face of the pink polytope. If and only if 0 is in the relative interior of the convex hull of 2, 4, 6. So 2, 4, 6. If I take the convex hull, you see 0 is in the interior. So whenever 0 is in the relative interior, then on the other side, you get a face of the polytope. Here's, for example, something that is not a face. So 1, 3, 2, 4, or 1, 2, 3, 4. This is not a face. And the complement of that is 5 and 6. So here you see 5 and 6. And 5 and 6, if you take the convex hull, 0 is not in the relative interior. Okay. So this is called Gale duality. It's a way to read off faces of polytopes from the dual configuration and whether 0 is in the relative interior. And it turns out that this is exactly what we need, because computing designs is really a problem on this side, on the blue side. But because of Gale duality, you can pass the whole story to the pink side, which gives you these polytopes, and the polytopes will help you put all these minimal designs on their facets. So that's the underlying reason why our main theorem works. And it has a lot of consequences. So as I said, one, it allows you to organize designs. So now we know how to think about designs. There's a notion of adjacency of designs, because like here, for example, there's a local picture of what's happening. So these are designs of the Peterson graph, starting with one design that's living on a facet. And then all the other designs that it's connected to are living on neighboring facets. So this is just a local picture, and then you have to like keep going around the polytope. But here you see locally how you can connect designs to each other. So there's a notion of adjacency. They're very well organized on this polytope. Okay, so that's sort of what the theorem buys for us. Okay, the theorem will also give you things like bounds. The details are not so important, but you can get theorems that say that for every k, there is a positively weighted k design of size at most something. This turns out to be useful, and this comes from this polytope connection again. Okay. So that's sort of the main content of what I wanted to say. And then using this theorem now, you can do all kinds of things. You can compute minimal designs, you can optimize over them, you can find the smallest one, you can do all kinds of things because we know that they live on these polytopes. So it turns out to be, in some cases, easy to compute the polytope, and therefore you can answer these questions. So that is basically the idea of the work that we did. So let me finish in the last maybe 5-6 minutes by just showing you one type of example that you can compute. And this is minimal or extremal designs on the graphs of hypercubes. Okay, so we worked on a few different families of graphs. They were all Cayley graphs. So this is an example of a family of Cayley graphs. So just the vertices, the edge graph of the 0, 1 cube of dimension d. Okay, so the graph I will call Q sub d. D tells you the dimension of the cube, and we're just taking the graph of it. The eigenvalues are very explicitly known. It turns out to be 1 minus 2i over d, and there's I going from 0 to d. Okay, so there are d plus 1 different eigenvalues. The eigenspace of lambda I is also known. It's D choose I. The eigenvectors that form a basis for each eigenspace. You can also explicitly write down, of course, there are infinitely many eigenbases, but there's a distinguished one that people use a lot that has a formula. It's very well known. These are actually characters of the group Z2 to the D, of the abelian group Z2 to the D. So this comes from representation theory. People know all of these things very well. Okay. So in this case, a lot of the spectral information is clear. And the question is, what are these polytopes and can we calculate designs? So there are, as I said, look, there are D+1 different eigenvalues. So I'm going to index the polytopes by the eigenvalue. So P0 turns out to be a point, not very interesting. P sub D, which is the last one, is a line segment. It's also not so interesting. But all the other ones are somewhat interesting. So when I is odd, the polytope is centrally symmetric, which means if X is in it, minus X is also in it. And it has 2 to the D vertices. And when I is even, this polytope has doubling, like you saw. So every column appears twice, and it only has 2 to the D minus 1 vertices, and it's more not clear what it is. Okay, so these are interesting polytopes. One of the polytopes that shows up, which is the P2, the one that goes with the second eigenvalue, is what's called the cut polytope of the complete graph. So this is a very famous polytope that encodes a NP-hard problem. And because of that polytope appearing, you can write down a complexity result. So you can say that, for instance, unless NP is co-NP, there can be no efficient description of all minimal positively weighted K-designs in a graph, because knowing all minimal positively weighted K-designs in this example would be the same as enumerating all the facets of the cut polytope. And that is not possible because the underlying problem is NP complete. Okay, so you can get complexity results that show you this is a hard problem. But what we could compute are some of the extremal designs. So the extremal designs, remember, are designs that catch all eigenspaces except the last one. So in this case, the last eigenvalue is sort of the middle eigenvalue, okay, in the sense that we want the index to be roughly half of D. So depending on the congruence class of D mod 4, the half of D that you're interested in turns out to be one of these numbers. Okay, the numbers again are not so important, but just think of it as roughly half of D. Okay. In this case, we can say several things. So for example, D equal to 2 mod 4, this case, this turns out to be easy. So here the minimal extremal designs are combinatorial and they have 2 to the D minus 1 vertices. These are these centrally symmetric polytopes. And these designs actually come from codes. They come from linear codes in coding theory. Okay, so they are linear codes. A linear code, if you may recall, is just a subset or a subspace rather inside the Boolean in vector space 0, 1 to the D. Okay, so if you think of 0, 1 to the D as a vector space over Z2, then a subspace inside that is called a linear code. It can be written as the kernel of a matrix or as the span of some vectors. So let's say we write it as a kernel of a matrix. And Catherine had proved this result earlier that said that if you have a linear code like this, then it'll average all eigenvectors indexed by x's that don't live in the row span of the matrix. Okay, so some small technical lemma. And then from that lemma, we can actually construct pretty small designs. Okay, so these small designs have sizes. So again, the details here are not so important, but what's important is that we can calculate them. They are fairly small. They have size 2 to the D minus T, where T is actually quite big. Okay, so 2 to the D minus T is quite small. These are small designs. They also come from codes. They come from generalizations of the Hamming code, basically. And for small values, we can prove that the Hamming code is actually optimal. These are the best designs that are extremal for the cube. But we don't have a proof that in general that it's always optimal. And then you see some numbers like this. So let me show you a couple of numbers. So here, for example, is the 7-dimensional cube. the 7-dimensional cube, the eigenpolytope has 128 vertices. And we're saying that there is a design that has only size 16. That means that this polytope has a facet of size 128 minus 16. Okay, that's a pretty big facet. So, and this turns out to be exactly the Hamming code. So out here, you see everything that we construct here pretty much are generalizations of the Hamming code. And these are very good designs. And our conjecture is that these are optimal. Okay, so that's basically everything. And the talk is based on this paper that we finished in April. And then if you, Catherine has a whole website with many, like a whole gallery of designs. If you'd like to see pictures, this is kind of an interesting place to see lots and lots of designs. If you compute any of them, she'd be happy to put them on the web page. So please compute and send if you find interesting examples. Thank you.
Thank you. Let us thank Rekha for her very interesting talk. Are there any questions? Can open your audio and video if you have any questions.
Yeah, please do.
So does this work only for regular graphs?
No, so you can define everything. You can define graphical designs in general for any graph. It's just that you have to worry about what the actual global average is. The regular graph allows you to just say, okay, the global average is 0, so let's not worry about that anymore and worry about the rest. The whole polytope theory does rely on regular graphs. So I'm not sure how to extend it to non-regular graphs, the structure of these eigenpolytopes and so on. We do rely on that because it relies on this dual configurations and so on, and that relies on the fact that you get 0 as the average value. But in general, the theory should, everything can be defined for general graphs, which is how they were defined in the beginning by Steineberger.
Sorry, one other question. So
Yes.
when you pick these eigenvectors, the scaled versions of the eigenvectors could give you, your coincidences are happening because you have chosen the eigenvectors in a certain way.
You mean the doubling?
Yeah.
Yeah, so the doubling, yes, so that's an interesting question, whether it matters. So what it turns out, it doesn't really matter. So the polytope, if you choose a different eigenbasis for the same, or different basis for the same eigenspace, then what happens is that the two polytopes you get will be related by a linear transformation. In fact, I think it's, by some linear transformation. I think it's even, it has to be invertible. So it's even a nice linear transformation. So the combinatorics doesn't change. So the embedding of the polytope will change, but not the combinatorics. So everything that we rely on, like the fact that the facets are indexing these minimal designs and so on, all that will be intact. Does that make sense?
Yes, thank you.
Yeah, and then Goetzel has theorems that tell you why you double. So he has some sort of, I don't remember exactly how it works, but he can tell you exactly when you will get doubling of these columns. He was interested only in one eigenspace at a time. What we need to do is stack these eigenspaces together and then take the polytope, but it's essentially the same definition as Goetzel. So I'm gonna just call them eigenpolytopes. So they've studied all kinds of things about them. They're mostly interested in the second eigenvalue because the polytope that you get is oftentimes the same as it's sort of the graph of that polytope is sometimes an embedding of the original graph. So they've studied different questions. So yeah, this is a new application of it, I think.
Yeah, can I ask one question?
Yes, please.
Yeah. So in case the group is a Cayley graph for some group, in that case, is there some nice action of the group on the polytope that you get?
Yeah. So in general, the automorphism group of the graph injects, I think it's no. So yeah, there's a map from the automorphism group of the graph into the symmetry group of the polytope. It's not surjective, but every automorphism of the graph, which you can think of as a permutation matrix, right? That permutation matrix maps to basically U, P, U inverse, where U is the eigenbasis of that particular eigenspace. So there is a nice matrix map that takes you from the automorphism group to the symmetry group of the polytope, which was also one of Godsell's big interests. I think the graph theorists were interested in things like that. They wanted to understand the automorphism group. For Cayley graphs, I think we should get a lot more things, but we don't really know too much about them. So it would be very interesting to understand more from the representation theory and the number theory and all kinds of things that go into Cayley graphs. But yeah, so everything we tried were Cayley graphs, but I don't think we are actually using the full power of Cayley graphs at all.
Right. And one more question is, so on this polytope, if you consider some point which is not extremum point.
Yeah.
So does this point say something like some information about some kind of designs, or?
That's a good question. So my guess is that so we are associating to one face, one design, right? So if we go like into the interior of the polytope, right, we really should get like the biggest, coarsest design. It should be the least interesting, and the most interesting are on the facets. Does that make sense? Or maybe I said it wrong. The facets are the most interesting, and then as you decrease the dimension of the face, it gets less and less interesting. Yeah, so I don't know what goes into the interior. That's a good question. I don't know how we would. This is just about the boundary of the polytope. Yeah. And just combinatorial boundary, really.
Thank you.
I have a question about the eigenpolytope. So we construct the eigenpolytope. Does the volume or the surface area of the facets, do they relate to any invariant of the graph that you start with?
I don't know. So a lot of people have studied these eigenpolytopes, not quite in the generality we need it, but just for one eigenspace, but that's also fine. But the types of questions they ask are very different from what I can tell. I don't know if anything like that is known, if the volume and so on matter. I mean, these things are not unique because you can change the basis of the eigenspace and you'll get something that's linearly equivalent. So then all these metric properties probably can change quite a bit. But normally the types of things they want to study are like, so people are interested in things like spectral drawings of graphs, right? So you can use the eigenvectors to draw the graph. So for example, will one of these polytopes will have the property that if we take its edge graph, the edge graph of the polytope, that is the original graph. So in that sense, you're getting an embedding of the graph in space as the edge graph of this concrete polytope that has vertices and coordinates and everything. So that's one very big important question that they've studied a lot, the graph theory people. But of course, that was not something that we worried about, because oftentimes we are not interested in, this is usually like the second eigenpolytope, and that's usually not the one that's last in frequency order or anything. Frequency order is weird. So it puts something very different from the usual type of eigenpolytopes at the end. Yeah, but there are many, many open things over here. So there are lots of questions to answer. It's very far from, we've just sort of scratched the surface. It's a new topic that really came from analysis.
So do these minimal designs help in integration?
So let me say a word about, they should, right? So that is the point of them, that they can help with averaging functions. And so this would be very important, for example, in things like graph sampling. So this is very, I think, used a lot in places. I'm not aware of, our results being used immediately, but so people want to do things like, you have data on some large graph. We would like to sample some small subset and make some decisions. Say, for example, we have medical data sitting on a graph relating, say, blood pressure or some other sort of medical information. We'd like to know, is there like a nice set of vertices I can sample and get a sense of the average blood pressure of people in this population? Maybe that population has some very specific qualities, like they're all above a certain age, or they are all, have certain characteristics, other characteristics. So this is actually kind of a useful and important thing, right? Like we have large amounts of discrete data. Can you find good sample sets from where you can get like global information about whatever function you're looking at by looking at a very small part of the graph? And if so, how do we choose such a small sample set? That's basically the idea of graphical design. It's also used in something called graph signal processing. So that's very much like Fourier analysis. So you have functions and you would like to on the graph, and you'd like to decompose them into these, by frequency, just like we do Fourier analysis. And you kind of want to get, sort of get the function up to some level of smoothness. So maybe we're not interested in getting all the components in the Fourier decomposition, but we want to get like, the smooth parts of the Fourier, the smooth modes in the Fourier decomposition. So that's another type of thing that people are interested in. It's called graph signal processing. So process the signal so that you don't take all of the frequencies, but just some initial frequencies. And that's what these designs will do, right? Because they can average the first few eigenvectors very well, or the first few eigenspaces, and that corresponds to smoothness in this ordering. Yeah, and then they have other relationships to things like random walks and so on, but still all very young.
Thank you. Are there any other questions? Okay, if not, let us thank Rekha for her very fascinating talk. We will soon announce the next talk in this series, and I hope you can all join. Thank you very much. Thank you, Rekha.
Thank you for having me.
Thank you.
Yeah. Bye-bye.
Bye-bye.